We have Matt Wilson talking about the spatio-temporal logic of agents, actions, and observables.
Okay, so yeah, thanks so much. It's 15 minutes, so I'm going to jump very quickly in. I won't give a massive outline of where this is going. We'll develop the story on the fly. So just to say, first of all, where we're going, this is based kind of mainly on a paper, recent paper called a BV category of spacetime interventions, which is in with my collaborator James Hefford. But this whole talk is built around a kind of more general, kind of wider program of research that we've been developing with a few people. So Timothy Hofferman, Julia Kiribella, Alex Kissinger. And it's generally a story about how we transition from simple kind of circuit theoretic models of computation, of the progression of the evolution of a state over time, into richer, higher order models of computation, of transformation, or of the kind of agent-environment interaction. So it's this transition from circuit model computation to agent-environment interaction that we're trying to study in a very abstract setting. And this agent-environment interaction, we tend to find, has a much richer logical compositional structure than simple computation. But to get there, I'm going to start with the circuit model. So there are a couple of convenient things the quantum circuit model gives us if we're people who are interested in causality. Not least, at a very simple level, the quantum circuit model for computation, it gives us a way to take gates, processes, systems, and compose them in the spatial direction. It also gives us a way to take the gates of computation and compose them in the temporal direction. Fair enough. And so there's a basic kind of spatio-temporal compatibility that the circuit model is giving us. It allows us to take our discrete dynamics and imagine embedding them in some kind of a space-time. The other thing that the notion of a gate gives us is a way of studying causal structure from a kind of information-theoretic point of view. So now I've kind of taken this entire big composed gate or process that's made of many little ones compositionally. I've made it into a big one, and I start asking about the causal structure of this big thing. And I can ask about this kind of information theoretically by picking my favorite input and asking if it can signal to some other output. And the way I can frame this is I imagine that I have an agent at the bottom that's taking some action. And the action that it's taking here is to make some choice of the state that goes in the bottom y. Okay. And then I imagine, for a particular y on the output that I want to ask about, I imagine that I have another agent who's taking an observation. And I say that there is signaling here if the choice of state by the first agent can influence the probabilities of various measurement outcomes for the agent at the top. This is kind of information-theoretic kind of causality based on a process. So there is signaling if the observations can depend on the choice of state, and then, maybe if I have something far enough away, maybe at a space-like separated point, I would expect to see no signaling in the process, no dependence of the measurement outcomes based on the choice of state at the input. Now, there's a nice compatibility between compositional structure of discrete quantum dynamics and their causal structure. In particular, the nice way around is compositional structure tends to imply causal structure. So for instance, I can see, going back to this original decomposed circuit diagram, the possibility of influence between one agent's choice of state and the other agent's measurement outcomes because of all of these possible time-directed paths from the first system from the input system to the output system here. In the same circuit diagram, I can't see any time-directed path in this diagram here. And this gives me an indication that there could not possibly be any kind of information-theoretic signaling between these two wires. Okay, this is a nice story, but there's many kind of information-theoretic facts about causality hiding in a circuit diagram like this that aren't easily accessible from this kind of input-output way of thinking. For instance, let me just pick 2 points that seem to be kind of in the middle of the diagram. They seem like they correspond somehow to events. They're there, I can point to them. And it's clear to me from the circuit theoretic structure, right, that there should be no influence between these 2 points. The circuit diagram seems to say this. There's no forward-directed path between them in the diagram. But information theoretically, there's nothing for me to latch onto. There's nowhere to make a choice. There's no dangling input to make a choice, no dangling output system on which I can make a measurement. And so, the way that this is resolved, typically, and this is what I'm giving is one motivation for moving from lower to higher order quantum information theory here. There are many. So say I have these 2 points. I want to study causal influence between them. I imagine splitting the circuit diagram. I imagine cutting holes into it, where I now allow the agents to make interactions. I've made space. I've made space for agents to make interventions here. Okay, so I imagine allowing my agents to take those interventions, and now I'm back to a kind of first order problem. I can say, well, the fact that there's no signaling from here to here is witnessed by the fact that whenever I have an agent on the left here taking actions, the observations of this agent over here can't depend on them. So I split the circuit, make interventions. And the weird thing that's happened here when I start trying to study the causal structure, you know, in the middle of one of these circuit diagrams, is that I've moved from thinking about a process as an evolution of a state over time, and I've moved into this higher order picture where I'm thinking about that same circuit, but instead as a transformation from gates or processes to other processes, right? Here, the input to this thing is a process, and the output to this thing is also a process. So this is one way of thinking about the transition, if you like, from the circuit model way of thinking, to a higher order way of thinking, where we're transforming processes rather than states. This is one of many ways to motivate going to a higher order picture. If you want to study indefinite causal structures, it's naturally framed in the higher order picture. If you want to study quantum processes with memory, non-Markovianity, you're pushed towards the higher order picture. If you want to generalize games to the quantum setting, it's natural to be pushed to the higher order picture. The kind of unifying thing here is that every time we're moving from the progression of computation to trying to formalize interaction between agents or agents and environments. Each time we do that, we seem to move to the higher order picture. Just a quick reminder, since we're here in kind of quantum gravity, one of the nice motivations for higher order processes is that we can formulate things that can't concretely be built out of these circuit diagrams anymore. I've gone now fully to just imagine, what about any kind of reasonable process that can send processes to processes? And one example of this is the quantum switch, which chooses a superposition of 2 different circuit theoretic structures. Okay. These are much more complicated objects compositionally than traditional gates. And so their composition rules are going to be more complicated than just this tensor product and sequential composition rule that we saw before. In particular, the state spaces just had one composition rule, the tensor product. Now when we move to higher order, we find that the logical structure, the compositional structure of our systems becomes a lot richer. And luckily, there are a load of kind of logical hammers awaiting in the field already, looking, in fact, for a nail that are suitable here. So in kind of formal methods in computer science, there's been a variety of logics put forward, and the one that I'm talking about here is called BV logic, which were put forward with the imagination that they have something to do with kind of the logic of space-time events. And so here in BV logic, we have, rather than one tensor product, we have now 3 tensor products for events. One which is saying, okay, I take my events and I make them space-like separated. One that says, I take my events and I kind of order them in time, I do something time-like. And a kind of co-location idea. I have 2 events, and I co-locate them in the same laboratory, and I can treat them, you know, my local operations are now joint things on them, as opposed to the space-like case. Yeah, thanks. So it's a very natural logic, and it turns out that higher order quantum operations are a model of this logic in a non-trivial way. For instance, the higher order maps of indefinite causal order can be applied to, to see this, recall that the higher order quantum operations that could have indefinite causal order can be thought of as maps on the space of non-signaling channels. Higher order maps with definite causal order can be thought of as maps on spaces of one-way signaling channels. And higher order maps which don't impose any kind of causal relation between two events can be thought of as higher order maps on the space of all possible always signaling channels. And these three kinds of ways of composing atomic spaces of channels give us these three distinct connectives in VV logic that would collapse if we were just looking at transformations of states. Okay. Now, this is a well-established story already. The work that we've been doing is based on a kind of surprising fact. The story that I've given you is very high level, seems to make sense pictorially, seems to be very abstract. However, the actual formulation of this story in practice uses a lot of mathematics that's specific to quantum theory, a lot of typically features of finite dimensional quantum theory, things like the Choi-Jamakowski isomorphism, for instance. And it's a bit surprising, given the high level at which this content can kind of be presented. And so what we're working on is trying to understand if whenever I give you a circuit model, you can construct a model of higher order operations that model the agent-environment interaction from it. Here, the story I presented, it's known to work for quantum theory and a few similar theories. And part of the reason we want to do this, well, there's two reasons really. One is we want to make a kind of closer connection to quantum gravity and quantum field theory, which is often supported by infinite dimensional Hilbert spaces. And so there, the formalization of higher order maps is much less clear. Or if we want to study causality beyond quantum mechanics, just as you can study theories with beyond quantum non-local correlations, we want to study the fundamental limits of causal correlations across all conceivable physical theories. So for these reasons, our aim is to try and construct these higher order, richer models of spatio-temporal logic, agent-environment interaction from basic circuit models, with the idea being that something all of these intended domains have in common is that they all form circuit models to begin with. Okay, and since we've forgotten all of the physical substrates, all the stuff being quantum, classical, whatever, in the wires and the gates, all we know is the compositional structure, and so the only mathematical toolbox that we have available to us is category theory, which is essentially the mathematics of pure bare composition with nothing else added. Okay, and so I'll just give you a very brief idea of how it works, and then I'll skip basically right to the end. The point in our way of thinking is to say, what is a kind of salient feature of interventions that can be framed purely in circuit theoretic language, purely compositionally. And the important fact really is that the set of all interventions that I can make somewhere is a set which is closed under applying pre and post processings to the environment. A set of inventions is basically always closed under pre and post processing. And so this is our idea, and we focus entirely on sets that have this property. And so in general, for us, a set of interventions is a set closed under circuits on an environment. And it turns out you can define higher order transformations just with respect to this property as things that can transform sets, essentially, whilst commuting with these circuit actions on the environment. And this is something that you see. Is my time over? Good. Yeah, okay, good. So I'll wrap up here and just say this recovers a load of approaches to define higher order maps in very specific classes of physical theories. It has all of the logical collectives that we're looking for before. If you want to know more about how we actually construct these, of course, chat to me. And it has characterizations beyond some finite dimensional informational theories. We can also use these ideas to get new definitions or well-structured definitions of higher order maps on infinite dimensional spaces. Of course, if you want to know more details, talk to me about it. I won't talk about the outlook, and I'll just say there is some. Thanks very much for listening. Okay. Sorry.
Great, thank you very much. Any questions? So, since there is a tiny bit of time, I would ask, actually, where does the observer enter into this? So you mentioned observations, but they're in the sense of, or maybe you can explain.
In this picture, I mean, when you're taking an intervention, okay. So when you're taking an intervention in a circuit diagram, right, you're making choices basically at the bottom, and you're making observations at the top. So you should think of this just like a quantum instrument, basically.
Okay.
Yeah, the observation is just the top wire. Yeah.
Fair
The intervention consists of both. Yeah,
So via interventions. Okay,
yeah, exactly. Yeah, it's coming by intervention. Yeah.
Thanks.
Okay.
Okay, let's thank Matt again.